Send me the link. Where is the Carol? Why there is nothing? All accounts. That's strange. Carol sent me. Carol. Here is, but I can use the same link. So yeah, this pass.
And yeah, this is
So it's not necessary to have some special access. Nie, przez mam HDMI. Zapnę HDMI. Ja. To musi...
Switch.
Ano, formatuję. Ja, wybornie. Tady dělám mute a jo, audio bude přes, jo, vidíme. Běží. Děkuji. Okay. So, I have to share my screen probably before the start. Or it's not necessary. That's a question. Гузел, посмотри, пожалуйста, в Discord. Там один товарищ пишет, что ему нужна помощь с инсталляцией.
Окей.
Поотвечай ему, если это возможно. Join. Okay, the camera is somewhere here. Sound should be enabled. And the screen should be shared. I expect. Share the screen, share it. Yeah. Yeah. So, yeah, if you need to connect your laptops under the table, you can find sockets so you can connect them if you need to charge them. Yeah. So, yeah. Sounds is okay. This is not necessary. So nice to see you here. And I hope that you will see that docking can be quite easy. However, it is intrinsically quite complex procedure. My name is Pavel Polishchuk. I am the head of the group of cheminformatics and drug design at the Institute of Molecular and Translational Medicine, where you will have an excursion today. So I will guide you this evening. So, and in my group, we work on different medicinal chemistry projects, and quite often we are not fully satisfied with available tools, and we run large-scale simulations like docking, molecular dynamics simulations, and further stuff. So that's why we try to develop tools which should be useful for ourselves for the first place, but they should be also useful for you as well. And I hope you will see this. So because we try to develop these tools and in an easy way, so we don't want to spend a lot of efforts to teach new students to apply these tools. So they should be quite easy to use. Unfortunately, all these tools are command line, so you should be a little bit familiar with the command line. And we mostly develop them on Linux, but they can be run on Windows as well. Not all tools, at least docking, can be run on Windows, but in this case, you will be limited in the number of available features. So that's maybe not that perfect for you as users. But on a Linux system, it's quite easy to run. And on Windows, if necessary, you can always install Windows subsystem Linux, Ubuntu inside, and then everything will go quite easy to do. So that's why we develop these tools. We have multiple of them. I will show you tomorrow those tools for de novo design, how we can generate molecules in a very fast way and chemically reasonable way. Today we will speak only about docking, and one more point is that, yeah, we develop like many other academic groups our software, but we still support it. So that's, I think, the major point. So we make this software easy to use, and we still support it already for many years, and still plan to continue this support, integrate new features, and develop them further. So these are not like a rocket science. This is quite classical pipeline, but it is fully automatic. So it free you, so you can push a button and take a coffee for an hour or more times. It depends on your task. So how is the overall docking pipeline looks like, and what could be an issue? You already heard during this workshop different messages. So what could be the problematic, what could be not. So pointer laser. Oh yeah, it's much better. So there are few parts, large parts in the docking pipeline. First one regarding the protein preparation. It's really tricky to prepare protein, and up to now, I don't know a fully automated pipeline which can fix all possible mistakes and do not create some new mistakes. Some pipelines are very good, but still there are possible issues, and we will discuss this during the protein preparation part. So there could be missing side chains quite often in X-ray structure. Flexible side chains are not visible. Flexible loops are not visible, so they can be missed. Sometimes these loops can be partially close to the binding site, and that's why you cannot ignore these missing residues, so you should remodel them. You can have also alternative coordinates for some side chains, for example, because it's not always possible to assign ideal coordinates for atoms. Sometimes you will see alternative coordinates. Protonation, it's a major problem for proteins. Yeah, for most residues, it's quite easy to predict. But for some residues, the most problematic residues, from my experience, is histidine, because it can be in different protonation states, in different automeric forms, and not always software correctly predict in which nitrogen should be protonated in histidine, or both, for example, in some cases. So this need your visual inspection and manual intervention. So this step should be checked. Then ligand preparation is also not that easy. So yeah, you can take a structure of a ligand, put in your docking program, like show it previously, but you should be aware that depending on the tautomeric state, protonation state, it will depend the output. And also, if you submit, for example, molecule without defined stereo configuration, what would be the output? This is also a question. Sometimes this was implemented based on the request of one of the user of EasyDock. So user want to just submit to the docking some quite raw data with salts, mixtures, and so on, and just want to automatically strip them during the preparation step. And we integrate this in EasyDock to address these challenges. And the main challenge is, again, the protonation. And we will stop on this in more details a little bit later. So how challenging is to predict what is a protonation state. Docking itself, it's quite easy. So you should choose a program, you should choose appropriate settings, and then you should analyze the output. Yeah, so this is a nice part, I would say, of docking, because this preparation part could take, if you do this manually by yourself, it could take you a lot of time, enormous amount of time, especially if you make large-scale docking. If you dock just one molecule, okay, you can draw it manually and protonate it even manually if you're quite experienced. But if you dock hundreds of thousands or even just 1,000 molecule, it's already not feasible to make this protonation manually. So you need to use some programs, you need to make some pipelines. The output which is returned by docking programs are not so, not in a fancy format. For example, they use some PDBQT output, which is not so easy to parse and retrieve. And there are a lot of these small issues which make this pipeline doing manually is extremely long. And again, since it is long, complex, people can make errors and mistakes. So here's the repository. So all this code is open source that we will present today. So we are contribute to open source a lot. This is repository. We have a link to documentation currently, which is quite detailed. Here is the overall pipeline. Yeah. Oh, that's interesting. But did you see nothing?
Yeah.
So what happens?
Hello?
Why?
Okay, so this is recording is running.
But
What do you need?
what happens?
I see. So can I? Where is the share?
No. Here I see the right window. It is a problem with projector. It's not with the stream.
Okay.
It's a problem with the projector because here probably the double.
Okay. That's your limits.
Yeah, definitely.
Knowledge about
Yeah.
at least not any longer.
Primary join mirror. Oh, sorry. Yeah. Sorry for that. So you missed so nice slides.
Are you actually saying something?
Yes, all the time.
Because it says that the audio is muted.
But it's my audio is muted. But it is written here
Okay, yeah.
on this computer. So it should be okay. Okay. Yeah, so just sorry for this mistake. You should stop me before that. So here is a overall docking pipeline. What is the possible issues? Here is the repository of the open source software. Here is the general scheme, how it is designed. So the software is designed in that way. So there are two major steps. The first step is the preparation of ligand. Yeah, audio is recording. The first step is the preparation of ligand. The second step is docking of this prepared ligand. This is done due to that you can prepare ligands once and then want to dock them to multiple targets or different programs or different settings. So that's why you can prepare these structures once and then use in all other further docking campaigns. And we will go step by step to all these points. So the general functionality of the EasyDock. So it accepts only command line. and it stores all input command line arguments in the database. So the main storage and the single storage of all data in EasyDock is a SQLi database. So everything is in one place. And it stores all input arguments, all input data, and all output data there. It is done to make your results first reproduce
ديسكريبسيون داكشي كامل قد
database and check whether which settings were used to dock these molecules, what proteins were used. So proteins will be stored explicitly also.
تبارطاجي في لينكدين
Grid
ولا
boxes,
تصيفطوا ليه
everything.
هذوك بعد هذوك اللي المومبر ياك اللي مانتيريسينك زعما ولا لينكدين ولا
So they're speaking. So I said, but I couldn't mute here. Okay, I can just call to Carl maybe.
واش عطاوك جوج تاع لي ليان فاش تكليكي كتلقى داكشي نيت صيفطوا لينا
Yeah, because if I will mute
شيكي
here, I will mute myself.
واش داكشي هو هذاك ولا لا نقراو
Yeah,
آه.
here is the
لا ماشي
recording.
هكاك في الاول كيطلع انا مشيت كليكيت زعما درت انجليش ولا هذا وما بقاش كيطلع زعما هو اللي صيفطات لي
These
كيطلع
are, I
صيفطو
believe,
تفيريفي واش داكشي
because
هو
they
هذاك
run
ناضي
this
ما
in
دير
parallel in another room, the same
بروفيل
session.
تكنيسيان
That's
ووريك
why they
المعلومات
should
ديال
use the computer there.
ما عقلش ما عقلتيش
Uzel, could you come to the office of Carl and check?
لا لا هي الاخطاء ما تيداروش
It helped. Okay, good, thank you. Finally, let's go. Yeah, unfortunately, sometimes we forget about this. So this is done just to make your results reproducible first. So you can always return back and check what was exactly used, and you will never forget about this. The second point why we store all data, all input arguments in database, that you can resume your calculation very easy. So because, yeah, in our experience, we can make docking on cluster, then we run out of time, they were interrupted, and how to restart it. In this case, in the case of EasyDock, you can submit just the same command, exactly the same command without any changes. It will means nothing. Or you can submit just the output database as an argument. That's all. And all arguments will be nevertheless restored from the database. Only few arguments can be replaced from the command line, and they have a precedence. We already fixed it. Thank you. So only few command line arguments have a precedence over the stored in the database. So in this way, you can just, okay, it is interrupted, you rerun the same command, and docking will continue. So it's quite useful for us, for example, especially for large docking campaigns, which could be interrupted due to some issues. Yeah, as I told you, it mainly runs on Linux, but on Windows, it's also possible to run this pipeline, but with a limited number of features. So here is a ligand preparation part. So what we implemented, as I told you previously, we implemented sanitization of input structures. Input structures can be SMILES, 2D SDFs, or 3D SDFs. And in the case, if you will submit 3D SDF, exactly the same conformer will be used as a starting point for docking. If you submit SMILES or 2D SDF, then the initial conformer will be generated by RDKit internally. So in this way, you can tweak, for example, if you need some specific starting coordinates for your ligand. So we perform sanitization and checking. We strip some salts. If there are some sodium, potassium, hydrochloric acid, whatever, they will be automatically stripped. Then, if your molecule have undefined stereocenter or double bonds, they will be enumerated, and you can specify using the command line argument -s how many stereoisomers you want to generate. Because this is useful, it's not always possible to generate all possible stereoisomers, because, for example, if you dock some hydro carbohydrates, which have many stereocenters, and if there are D3, those units, 2 or 3 those units, the number of possible stereoisomers is incredibly large. And this generation will take minutes probably, and then docking will take hours. And in this case, you just specify the maximum number of stereoisomers you want to generate for compounds having undefined stereocenter and double bonds, and they will be generated. If you not specify anything, it will generate a single stereoisomer, and the generation of stereoisomers are always reproducible. So if you will generate them for the second time, third time, starting from the same structure, you will get the same output. So we try to make this pipeline reproducible in the terms of generation of stereoisomers as well. And the last point in the ligand preparation is the protonation of these molecules. So we tested multiple approaches. We integrated some of them, and I will show you later this comparison. But currently, there are available some open source modules, SmallGPK, PK Solver, and UniPK, and commercial software Chemaxon. But some other could be integrated as well by request, or if you want, you can do this by yourself and contribute back to the repository.
But it's usually used with Miko in generating the PQR files. So you have, because this was the one I'm typically using, so I'm wondering.
But I'm not aware that they are used for ligands as well.
No, sorry, this for only ligands. Okay.
Yeah. These are just for the ligand part. Protein part we prepare manually because protonation, no. Protonation, Miko cannot protonate molecules. But it's not a hydrogenation, so it's not add hydrogen. It's generation of a protonation state, so charges, how charges will be in your molecule. So what are the plus, minus, and so on. So it's another story. And for protonation, we use these tools, and new ones can be quite easy integrated. And the docking stage, it also has multiple features. Some of them are not so frequently used, but quite useful. For example, like docking of boron-containing compounds, because quite a lot of programs still cannot dock and process boron in small ligands. So they will just return you an error and stop processing. We implement on the fly replacement of a boron atom with a carbon. Your molecule is docked, returned back from the docking program, and the carbon replaced with boron backwards, and the structure stored in the database. And this replacement is, as we showed in our publication, is reasonable because it performs pretty well in redocking experiments with Autodock Vina, with Gnina as well. So this is quite reasonable. This is not our invention. So this was published something like almost 30 years ago, whereas first docking programs appear, because boron and carbon, they have very similar atomic properties. So that's why they could be to some extent interchangeable for docking programs. So that's why this works. Yeah, we implement this feature just because we need to dock several hundred of boron-containing compounds, and we couldn't find a program which can do this. It's not so frequently used. So as I told you, initial conformation will be generated by RDKit if necessary. Also, we implemented optional feature like additional sampling of ring system, saturated ring systems, because usually docking programs and those docking programs which we integrate currently in EasyDock, they consider saturated cycles as completely rigid. So it completely depends, the geometry completely depends on the initial geometry of your ring. So if it is a chair or some other bath, some twisted conformation of a cyclohexane, it will be in all derived poses. And especially, for example, again, for carbohydrates, it's not so reasonable because you may not expect that the generated just single conformation will really satisfy the requirements of the binding site. So in this case, we implemented a procedure when we generate multiple conformers, then we cluster them and take representative conformers, just few, based on the coordinates only of ring systems, to sample ring systems. Yeah, this and all these initial conformers are docked in parallel, so this increases the computational cost proportionally. So usually in the large databases, if you enable this option, it will increase the time something like 2-3 times. So, but it is quite useful, especially if you work with the large saturated ring systems. Yeah, docking agents which we support, they're listed here. They mainly belong to the Vina family with GPU, Quina, whatever. Also, we support Gnina, and through Gnina, we support Smina scoring function as well. Also, this pipeline can be run on a distributed environment. So if you have multiple servers on your cluster, you can run a single job on multiple servers simultaneously. We support this feature through the Dask Python library. We will not discuss this today, but if you are interested, you can read in the documentation. Sorry, my voice is you require some water. Yeah, for this distributed computing, we propose a prioritization function which specifically predict docking runtime for each molecule. It's very simple. It's based on the linear regression and on two descriptors, number of heavy atoms and maybe molecular weight, I don't remember. So it just predicts the possible runtime, and based on these predictions, we try to balance the utilization of your servers to run them almost evenly, distribute those computation. And the output of these docking programs will be automatically converted to mol format and stored to the database. Okay, here is our comparative study, small comparative study which we did because protonation may affect sometimes quite significantly the output because you have some additional hydrogens or not. And this can be additional hydrogen bonding detected, and this may affect the docking outcomes. So that's why we tried to choose which protonation tool could be the best one. I do not say that we found this tool, this magic bullet. It's maybe not possible. You can find in the literature, I forgot to copy the table from one of the recent papers where they review multiple approaches to predict the pKa of molecules, small molecules, and this table shows that all tools perform very, very, very well on sample challenge data and on Novartis data set and other small test sets, which are quite commonly used for benchmarking. And yeah, they can really very good predict those structures and those pKa values, but these data sets are quite small. And I didn't find any wider evaluation of these tools. And when we start to use these tools in practice, we found that many of them fail on very simple examples. For example, as it was demonstrated in a presentation of Rowan Science, piperazine, simple piperazine. When you ask to protonate, most programs will protonate both nitrogens. But at the pH 7, it's not possible, physically not possible, because many programs, they just disregard the mutual influence of atoms in molecules. So they just predict pKa, disregarding all other part of a molecule. So that's why these predictions cannot be used to estimate the protonation state, the most preferable protonation state. And okay, we found this and many other errors, a lot of errors. Phenols are quite often, even those physics-based models like Cupcake, they fail. They fail on piperazines example, they fail on phenols, so they often deprotonate phenols, and yeah.
What is the importance of the protonation? What is the importance of the protonation during the docking calculation? If, for example, we miss one hydrogen in some parts, this can affect really.
It may affect, yeah, it may affect, because it's like additional anchor for your ligand. For example, you have a hydrogen, or your carboxylic group, it has a hydrogen. Then it may be not that will be happy to look, for example, to lysine residue. But if you will this hydrogen remove, it may find the connection. And this is the problem. So if you will not deprotonate molecule, it will not find the proper orientation, and then ligand may flip and try to find some other partner which will satisfy this hydrogen bond donor interaction. Some of them more sensible, less sensible, but generally yes. So without some additional tests, you can never be sure that the protonation states are not important. For those, for example, again, presented already, and those bolts and other tools which predict by the co-folding the binding pose of a ligand, they disregard completely hydrogens. And then when you will reconstruct the correct structure, adding hydrogens, you may find quite interesting situations when you have two acceptors looking to each other or two donors looking to each other from the ligand and protein part. And this means that, okay, this is just irrelevant. And if you will repeat the docking, the structure may flip or fly away. It's difficult to predict. So proton... It could be spherical, yes, but with protonation, it's mainly due to the hydrogen bond network, which can be formed inside the cavity. Because, for example, vena, it completely disregards charges. So you can submit charged molecules, but it doesn't count on that. But vena counts on hydrogen bonds. Some other programs may be more sensitive to charges. So if you have some formal charge on an atom, some other program can take it into account. I don't remember whether whether Gnina took charges into account. I don't remember. But some new programs can do that. And it will also be more difficult for them if you will not submit proper charges for such programs. So that's quite small, but could be important. So could be important. But each program should be tested, of course. Maybe some of them could tolerate this issue. I don't know about such programs. And how we tried to evaluate those available protonation approaches, we took Wall-Campbell. We selected compounds with up to 500 Daltons molecular mass just to be in the drug-like chemical space, and we predict protonation states by Chemaxon. Chemaxon is a well-known commercial software to which we trusted before, and currently it's okay, I would say. But since they became already known for free for academics, we started to looking for replacements, and that's why we initiated this study, this small study. And then we generated, for the same structures, protonation states using other approaches, which are listed here. And here you can see, for example, open bubble. Here is the overall number of compounds was 1.7 million, but for many of those compounds, protonation states didn't differ from the initial one. So neutral molecule remain neutral after prediction. So it doesn't have ionogenic centers. That's normal. So this is a number of molecules which were changed at least in one of these programs. So in almost 1 million molecules, at least one program found some ionogenic centers. Here is a number of structures which were unchanged after protonation with open bubble and agree with chemaxon. Here is a number of structures which were not protonated by open bubble, but protonated with chemaxon. This one, yeah, it's better for online to show here. So this one. This is a number of structures which were protonated by open bubble and changed their protonation state. And here is how many of these protonated structures differ from chemaxon, which were changed. And here is the overall number of structures which disagree with the chemaxon, the last column. And you can see that the number is quite large, so relatively to the starting. So less than maybe quarter, more than quarter of compounds disregarding. Okay, maybe it's not a problem, maybe some other programs even worse. We tried MolGPK, which is a neural network, quite fast working. We integrated it into the EasyDock, and when we run its original implementation, we found that, okay, the number of disagreements in this case is less than for open bubble. Okay, it seems already better. Then we tried to fix we analyzed the output and tried to manually fix typical errors. So we crafted by hands some rules which apply after protonation to revert back some obviously wrong protonation states. And after these fixes, we could improve the prediction and achieve almost 200,000 differences with chemaxon. And then we tested also PK solver. It was developed in Thierry Langer group many years ago. Not many, but quite a lot. And unfortunately, it failed even worse than open bubble. And it did a lot of strange things. It protonate amide groups. There are many mistakes. So we tried to also fix it in a manual way, but it is too hard. Then we used recently discovered on the GitHub repositories PK predictor. And in this case, a number of different predictions, even worse than open bubble. And the most recent finding and our testing and integration implementation is a UniPK model, which worked out of the box quite well from the very beginning. So yeah, it's still not perfect. Again, chemaxon is not a true ground truth. So it's also not a golden standard. We don't know whether it is correct or not, but we trusted to chemaxon quite a lot before that. So that's why we try to find the correspondence between those programs. Were also a lot of discrepancies, so they are not overlapped tightly in their predictions. So I skip this because otherwise we will not reach the tutorial part. And here is just few examples of structures which are quite often ionized by chemaxon, but not ionized by UniPK. And you can just see, for example, this structure, yeah, it is deprotonated nitrogen in this position. And as a chemist, for me, it's quite difficult to estimate whether it is really true. I'm suspicious that maybe not. And this is a mistake of chemaxon. In this case, it's probably true. In this case, I'm not that much sure that this nitrogen will be protonated. at pH 7. In this case, yeah, I would agree with Chemaxon prediction. It is reasonable. This one, 50-50, I would say. So these are just few examples. There are many more examples. Even we found some examples where Chemaxon not protonate obvious centers like primary, secondary, or tertiary amines. So you have a piperazine ring with the aliphatic substituents on nitrogen, and it didn't protonate it for some reason. The same we observed for UniPK. Sometimes we observe doubly protonated piperazine rings. But the number of these cases for Chemaxon and for UniPK is much lower than for other tools. So that's why we currently suggest to use UniPK model for protonation, but it is slower. So it requires more computation, and that's why it is slow, because it enumerates all possible microstates, predict free energy for all microstates, and then aggregate those predictions in a single value to return you the most probable protonation form. Another study, some micro study which we made, it's investigation how much sampling of ring system may affect accuracy of your docking. In these cases, we extracted, I don't remember exactly, less than 2,000 structures from PDB which have ligands having saturated ring systems, at least one ring system saturated. And then we perform docking using Vina and Nina for those cases. And as a starting position, we used either the energetically lowest conformer, or we additionally add to this the lowest conformer, additionally sampled conformer for each molecule. And what we see as output, that if in both cases for Vina and Gnina, if we add additional sampling rings, and then when we dock all these conformers with additionally sampled ring system, we select as a final prediction that conformer which have the lowest binding affinity predicted. So just one. And we say that, okay, this is the output of our pipeline. So in database, we do not store these intermediate conformers. So only the survived one. And when we analyze those survived poses and top poses returned by the common procedure, we found that we could increase the number of successful redocking. So the molecules which are redocked in the way with additionally sampled ring systems could better orient, so we can reproduce for these structures their crystallographic position. So this is just confirmation that this may make sense, but at the additional computational costs, 2-3 times more. Okay, so now we can finish the theoretical part of a presentation of the tool. Do you have some question regarding this part, theory? No. Okay, so then let's go to some practical part. For preparation of proteins, yeah, we checked PDB Fixer, we checked some other tools which try to prepare proteins automatically, but we always found some mistakes. And that's why, nevertheless, we recommend, if you use any kind of tools, to check, visually inspect those structures to be sure that you have, at least in the binding site, everything is okay. There is no distortion, some strange coordinates, and so on, clashes. And we use most often Chimera. It is installed on your computers. I checked it. Unfortunately, the version installed on your computers is pretty old, and it may not work completely properly. And we will go. That's strange. Really strange, but okay. Yeah, I would suggest first let's to download some files. Oh, actually, it is good. No. What happens? I have to fix. And then conda activate rem add9. Okay. So these are commands which you should execute in your Linux shell. To run Linux on those computers, you go to the start menu, start typing Ubuntu, and on all machines you can find Ubuntu, you run Ubuntu, and you will see the command line interface.
So I could see, and cram add, basically I need the environment for EasyDock, right? Because that's hidden inside the cram add environment, or?
You mean your PC, you mean your laptop?
Yeah.
Yeah, you should be install it.
Yeah, no, I have it, because you're writing the cram add line, so I assume that's for the reason to get the environment.
Yeah.
Okay.
This environment, if you install it according to the instructions, then you have it. I provide the instructions yesterday, probably evening, night, or today morning, I don't remember. So everybody succeeded with running Ubuntu? Just to see the command line interface? If so, then you're currently in the home directory of a user in your Ubuntu, and then you can create a new directory typing the first command. I can make it larger if it is not well visible from the further rows. It's not that much, so let's try to increase the font size. Yeah, something like this. Yeah. So you type mk dir space then tilde slash add9. And this will create a new directory in the home folder. Yeah.
Because I did one complement from the GitHub. It's the same libraries. Yeah, it's the same command because I did it right now.
But you don't need it. So everything is already installed. So on these computers, everything was already installed. You don't need to install something new. Everything already prepared. Environment, everything. So
I need it.
yeah. Just activate the Ubuntu and start to execute this command. So first, you will create the directory. What?
Test cannot create.
Cannot create. Wow. File exists. Okay, file exists.
Okay.
So somebody already created on some computers this directory. Okay, if the directory exists, okay, let it be. If it is exist, you can switch inside the directory using the command cd and the path to this directory. Oops, sorry. Some questions? Oh, so many people works on their laptops. And do you have Linux on your laptops? Yeah? Cool. So it's really simplify things. So everything is fine? Not? So you didn't install?
No, I was trying from the GitHub here, and then in the AVB, and
Yeah, it should be possible.
so it took a long time. This
Yeah, this
and
is
I didn't install like the frame and
yeah.
Windows one. Frame and-
You try, but you have Ubuntu, so you should use. Yeah.
yeah, this
Yeah, it takes installation, but it will be successful, I believe.
okay.
But it can take 5, maybe 10 minutes. You can use Mamba
Mhm.
for installation. It will be a little bit faster to solve the dependencies.
Yeah, I was trying that as well, and it's still loading. I don't know, but I have internet.
But
only
no-
Mamba.
Additionally, you just
Ah.
have to write
Mamba by default is not available in Conda. So Mamba should be installed in the base environment first, once in the beginning.
Ah.
So if you don't have it, you should type while you activated base environment, conda install, c conda forge, Mamba,
Yeah.
and then using Mamba install other environments.
Enter.
So yeah, it looks a little bit complicated, but this is the most complex commands you type, maybe, because they're most cryptic. So you switch inside the folder and then you type this command. Sorry, I have to. I will make a PDF file and I will drop it to the channel of Discord, and then you will be accessible to command just to copy paste them. You don't need to always typing. It's not reasonable. In the beginning, yes, but in that case, it could take quite a lot of time. So let's try. So there is a channel, EasyDock, and then copy from teaching. Up, happens. Up. Okay. Teaching. Oh. Tutorials, document. Okay. So now you can open these slides as PDF and just copy paste from PDF those commands. Do not bother with typing of all these long commands. Sorry for that, I forgot. Yeah. So you create the directory, then you go inside this directory, and then you can copy paste this command git clone and this link. And it will download all files stored in the repository on the GitHub directly in this directory. And you will see then, how you will see. In this case, if you want to list the directories of files in your current directory, you type double L, small L, and press enter, and it will list you the available files and directories. And if you will do this after the command git clone, you will see that a new directory will appear named EasyDock Creme Tutorial. And inside this will be all files.
Wondering if you know Unidoc, because it's from the same team that basically did the UniPKA prediction stuff, and they have CUDA accelerated docking, which they claim like usually to be faster and better than Vina utilizing GPU. So I just wondering if you knew it. Like this one is a fairly new version, but I have
think
experience
not.
with their older version of Unidoc.
Mhm.
And they have like very nicely benchmarked all of the stuff, and it's worth looking into, in my opinion, as I kind of like it. So just saying.
That's interesting. It's Unidoc from Unimol. Okay, we will look on that. But do they have integrated those pipelines for preparation and processing and analysis, or they just dock?
All the Unidoc, I don't know for the version 2. I just discovered they also had version 2 now.
So they have protonation as well?
No, but you talked about the protonation. It's from them, the
UniPK, but yeah, I know, but UniPK do not return you protonation states. It returns you dash predictions.
It's found something else, and then just of the SDF they create. You create.
We have to check. We have to check because again, the idea of this pipeline is that it is unified interface to multiple programs. And another option why we developed this tool, I forgot to mention this, that they can be integrated in Python software in just one command. And this enable easy integration of docking in a third-party software you develop, and we actually use it in our further development. But EasyDock we will check. We can check how it can be useful. Can it contribute to this pipeline somehow? Okay, so git clone. Everybody succeeded with git clone? No. Okay. Do you need help? Do you need help?
I'm here.
Is it okay?
Yeah, then next step is the username and password, and that I will not didn't succeed. Okay, but I did this.
What?
Well, right. This is correct, right?
So nobody. I will check. It could happen only if the repository is private, but it's not possible. I checked this before. Yeah, it's public. It's public, so it should work. Then it should not require you the
So there's nothing wrong.
password.
Then I type conda activate cam. Is it wrong? This is correct. right?
But
I put some.
no.
L-
Conda activate is not necessary.
No.
It's-
Okay,
but it shouldn't ask you at all.
Okay, so then it.
Here is a mistake, but you just copy paste. So there is a misprint. That's why. Because maybe you have a Czech keyboard. So yeah, easy. Y. It should be Y. Here. Okay. Here. You don't need to delete everything, so you can just go in this way and then Y and
No.
yeah, because you need it's
keep-
English. So Y is here. No, okay.
EasyDock.
So
Keep-
EasyDock and Git at the end. That will. EasyDock. Yeah.
Doc.
Just Control C to cancel and to pause the last and then go
Yeah.
K. Yeah, K. Yeah, enter.
Okay.
That works. So now you can list WL
Mhm.
and it will list you. Okay, there are some directories inside. Is everything okay? And for you? You think or you're sure? You could install it by yourself. Cool. Cool. Thank you. And at the last.
But maybe
Everything works for you?
Yeah.
Yeah? So, and you also use Linux. Cool. Okay. So, and now you can activate the Conda environment and we will use it later. So this is the first, so Conda activate and the name of the environment which was pre-installed on these computers. If you install it from scratch on your laptops, the name of environment should be the same. If not, then just ask me and we can check how the environment can name. Or you can ask Guzel for help. Yeah, sometimes the main differences, for example, from commercial software, yeah, you have to set up a little bit this open source software, but once you set up it, you can use it for many years quite stably. Okay, so you, I hope, activated the environment successfully. If not, we will have time to fix it. You can ask Guzel to help for that, and I will continue with the protein preparation part. You can try to do the same steps on your computers and laptops. Again, if you have installed Chimera on your computers, or you can on this computer you can run Chimera. It's pretty old. I'm not sure that it will work properly, but you can try. What else? You can remove those, for example, files from this directory. Yeah, before that, you can remove these files from ADD9, not from ADD9, but from this EasyDock CREM tutorials directory, keeping only smiles maybe, to be not confused with the files which we create, because currently we download all files which will be even created during the tutorial. So if you want, you can just move them to another directory. To do that, on Windows machines, who are working on Windows machines, there is in a browser, file browser, you can go in this left panel to the very bottom. There would be Linux. On Linux, you can find the directories, and you can move this through the Windows. I cannot show. Yeah, I cannot show on my Windows because I didn't install Linux inside Windows inside Linux. It's too much. So. Or you can keep these files as is, but when you will create new files, those files, the old files, will be just rewritten. How to proceed with the protein preparation? So I will also run Chimera in here. I personally do not like interface of Chimera a lot. Oh, it's almost not visible. The resolution is too small. Okay, so I will try to describe in detail. So you go to the files and fetch by ID, and you can type 3RAL. So we will work with this protein, 3RAL. This is a CDK2 kinase in a complex with a active ligand, active inhibitor. And you can, in this way, download it to your computers. You may not repeat all these steps because all files were already pre-computed. At least you can, I can show you how the preparation part may look like. And you can go already when we return to the command line, we can go with further commands. So we can click fetch, and in a second, we can see the structure, ligand, protein. It's quite simple. There are a few water molecules. You can see some missing loops. Here is dashed line, designates that between these two parts of a protein, there should be some amino acid residues, but they are not resolved in X-ray. But since they are far away from the binding site, we shouldn't be bothered about them. So for docking, we can forget about this. But for example, when you prepare structures for MD simulations, of course, all residues should be reconstructed. And what is good in Chimera is that they have, sorry. They have quite automatic preparation part. And for this simple protein, this preparation part will be enough, and quite often it would be enough. And to call this pipeline, you go to Tools, Structure Editing, and then Doc Prep. Yeah, it's not very well visible. And then there are multiple options which you can choose. So delete solvent. By default, we usually delete water molecules. But again, if you know that some water molecules are important, then keep those individual water molecules and they will be a part of a protein site, of a protein partner in docking. So delete water molecules, delete ions. In this case, we have no ions in the structure, so it will not affect this checkbox. Then for alternative locations, so it checks, and in this structure we have some alternative locations for some residues. It means that coordinates are not well defined, so that's why we have two possible positions for each of side chains, and it will be automatically keep the most populated of these coordinates. Only one form will be remain. Then we can keep these checkboxes. Then we can enable checkbox on complete the side chains. So if we will keep it, then side chains will be automatically reconstructed from the library. Then definitely we need add hydrogens. Chimera has its own implementation of the protonation of proteins and ligands. Then charges we don't need, so it's not necessary to add charges because Vina disregards charges as many other programs. But for example, if you use EasyDock, not EasyDock Vina, but EasyDock 4, for example, it needs charges. Maybe some other programs as well. And you should disable write in mode 2 file because we will work with PDB. So just keeping these checkboxes, remove water molecules, keep the most populated alternative coordinates, protonate, and reconstruct missing side chains. Click OK. Then it asks you which protonation state to choose, how to protonate your molecules, and for histidine, it's safer to choose unspecified, and the protonation state of a histidine will be detected based on the hydrogen bond network, which is observed inside the protein. And then click OK, and everything happens in half a second. So I think that you have some problems with something else, yeah? Not with Chimera. If you have some questions, you can ask me, so we can try to go. Yes, just a second.
Chimera isn't working here or here. Should I run it from Windows? Like so?
Yeah.
Yeah,
Yeah, unfortunately, it's too old version. I discovered this just yesterday, and you could not reinstall everything, so that's why Chimera may not run. But on some machines it runs, and some machines it not. So we didn't test all machines, so that's why it's difficult to predict. So do you need some help?
Yeah, I think it.
Try to file, fetch by ID, then type 3RAL.
Yeah, it's long.
R, it doesn't matter, capital or small letters. Okay, fetch, yeah. And okay, fetching is so long. Yes, the old version of Chimera, they cannot connect to the website of PDB. Yeah.
So we need to download this.
Yeah, in this case, you can download the PDB file, but this PDB file was already... No, I didn't. Sorry, yes, this is the problem with Chimera. Okay, so in this case, I would suggest to skip this stage, at least for your site. So you will just see, because we have all prepared files which we downloaded from the repository. So we have a protonated protein, and I will show you just how to do this, and you can look how it works. Yeah. Too many software, too many pieces should be linked together, and not always all versions are satisfied each other. Yeah, so setup can be difficult, but then usage for free. Or you pay money and obtain the same pipeline from a commercial company. So we protonated our structure, and then we can save them using some selection residue standard amino acid. So it highlights protein part. We save separately the protein part. We save separately ligand as a PDB. And then in your directory, you should see something like this afterwards. So there should appear the PDB ligand and PDB. So there should be two files appear like this one, protein and the ligand in the PDB format. So this is you already have in your repositories, which you downloaded. Okay. Ooh, terrible. Okay, we can make it maybe maybe better to close to make this one smaller and this one larger. Okay. So currently you're in the directory of ADD9, and you can switch to the directory similarly like me, if you hear me. Okay. So you can type cd, then EasyDock -crem -tutorial /9add raw, and you will switch to the directory with all files you just downloaded. But in my case, the path is a little bit different. In your case, it should be just cd and this part. We'll just make it even larger to be more visible from the last rows. And in this case, you will go inside the directory you downloaded, and when you will make ll, you will see more files, because I remove those files which we store in the repository, because there are output files as well. And in my case, I see these two PDB files and two smiles. Smiles we will use later. Currently, we are focused on PDB structures because we prepare the protein. So could you switch at least to this directory? Yeah? Did you succeed?
Yeah, the Chimera doesn't work.
No. Chimera, you can forget about Chimera. So we are skipped and then go as cd, EasyDock, crem, tutorial, and so on. So we have to go inside this directory. Actually, to better visualize, to better understand the structure, I just show you one command. For example, this one, and then you type tree and the name of and you can see the directory structure with all files, how it is looking. So we should go inside the EasyDock crem tutorial, inside 9add, and inside 3raw, using this command. Without this ending. So just go inside the directory, and we can continue in something more pleasant. I also like graphical interfaces, but sometimes they're too complex to use them. So you're almost there. Just cd. It's not necessary to Python. As I showed you the command cd EasyDock, just start to type in cd. Oh, no. In Linux, capitalization of letters is significant. So use exactly the same letters as in command. Then you start typing easy.
Contains one.
So you didn't clone this. So you can just check nothing. So you should copy, go up. This copies all this line, git clone. And копировать this one. And then insert, right button, okay, enter.
Yes, it is.
No such. No. Okay. Once more, copy. Copy. Yeah, this one. And once more, because it didn't copy the whole string. Yeah. So it will download it. And now you can type cd. And you start typing the ER and then tap. One again, begin, tap. That's all, enter. And you're already inside this directory. And then ll, and you will see all these files here. You have more of them because they're already prepared. So did you succeed?
Yes, we both succeed.
Both. But nevertheless, it's always good to have such a good friend who can help. Especially when you started to work with Linux. Is everything okay for you? Cool. For you as well? Good. Perfect. You as well. Okay, you are here. Okay. You are virtually here. Okay. Yeah. Yeah, sure.
After all installation, so I imported Torch. How do I proceed again?
But if everything works, then you have to download this repository through the git clone. Did you already do this? Then go inside.
And D2, 3.
Yeah. Up to this directory, and everything should work. Just tab will help you.
Tab. Okay.
If you start typing,
Yeah, because
it will automatically auto-complete it.
okay, so then 3.
Yeah, enter, and it's just LL just to check that everything is okay. LL, double L, enter. Yeah. So you list the files you see. So we will start working from this 3 RAL directory. Okay. And we have to convert this PDB structure into the PDB-Qt structure, which is accepted by Vina, Nina, and all these tools which are currently integrated in EasyDock. So we go back here and so here you can see, it's not visible again. Yeah, it should switch. Yeah, here you can see the command. So for conversion, we will use, it's so small, started to be so small, this pointer. So we will use Miko, which is already quite well-developed module, Python module, which helps you to interconversion between those PDB-Qt and other formats. And here, below, within this orange box, you can find the whole command which you have to execute. So you can copy-paste the whole command if you activate already this crem ADD9 environment, it should perform and it will return you some output. And while you're doing this, I will explain you what this command means. So I will collect all pieces together. So this is the command from Miko. It will be automatically executed. Here is the input PDB file with a protonated protein structure as input. Here it is. So these commands are identical. They are just split on lines to explain each argument, but you should execute the command from the orange box. So here is the input PDB file with a prepared protonated protein structure. Then output is the base name of output files. So this is just the prefix of those files. -p means that you want to create a PDBQT file as output. Then I inserted here the wanted alternative location in a specific format I specify because Chimera, it strips those alternative coordinates as I told you, but it kept their IDs in a PDB format. That's why Miko recognizes this as a okay. Probably there are more than one form for this sidechain. Actually not, but currently Miko cannot do this and process automatically. I already submitted the issue and they responded that they will fix it in some future. So here we specify the ID of a chain, then ID of amino acid residue, and this ID of the form, which we should keep A. For this amino acid, we should keep form B. For this amino acid, keep form A. Maybe for other proteins, you will not have such issue. Maybe yes. Nevertheless, this script, if you will execute, it will quite detailed inform you about possible issues which cannot be fixed automatically. So, and then you can address them manually, those issues. Then if we, at the same time, we want to create a docking box within which we want to make docking. For this, we specify the protein, the PDB coordinate, the PDB file of ligands, which were stored as well. And around this ligand, we will take the space with additional 5 angstroms from each dimension. And V-V means that we want to save this box txt file with the information about the docking box. So if you execute this command, in that directory, 3 new files will appear. But if you didn't remove the previous files, they will be just replaced with the new ones. And they contain, the first one, PDBQT, is a protein. Second one, txt, contain the coordinates of the docking box, and 3ral.box.pdb contains the specific structure for visualization. So if you open PyMol, if you open PyMol on your computers, it is also available, but I will show you how it looks, where it is. So Chimera, okay, PyMol. Then we have, I didn't execute this command, so I have to execute it, but okay. I can simply take it from here. So let's imagine that I executed this command. We can open PDBQT or PDB files, doesn't matter. And when we will open this .box.pdb, we will see the center and the coordinates of this box. Yeah, this is not maybe the best visualization, but this is what Miko proposes, and it's enough to understand in which region docking program will look for the possible placement of a ligand. And if you open the ligand in PDB-QT format, you will see that, okay, it exactly in the center of this box, and 5 angstroms to each dimension was added. So it is pretty large. Usually you should, again, from practical point of view, you should always decide what the size of the box should be. It shouldn't be too large, because otherwise ligands can start docking outside of your of your binding site. It may also happen. If you make it too small, large ligands will not fit to the docking box, and then it will be penalized by the program. Okay, so we have already some preparatory steps. Then the last things what we need is a structure of a compound we want to dock. In this case, I choose to dock the same ligand as in the crystal structure. So it's a native ligand from this crystal structure. It's SMILES. You can find this file in your directory also. And here is a configuration file for EasyDock, where you specify details for the docking programs, which are integrated. If you want to use VINA, you specify the path to the protein. Actually, yeah, in your case, you should edit these files.
Can the path be relative, or do you need to insert like use the
It can be relative, but I would advise to use absolute. It will be safer, I would say, for future, because if you run it from another location, there will be an error. But yeah, it should accept. Okay, I will also switch to this directory. Okay, and then I will copy here those files which you have, like config and SMILES, they're already inside. Okay, so here we can see that, okay, config VINA, I have it, and you also have it in this directory. And you have to fix these paths. So you type nano and then name of the file. Yeah, that's needed to. So nano and the name of the config VINA YAML file, and it will open you in the text editor. Oh, sorry. It's so terrible. Chat request notes. Video panel. Okay, and here you have to just replace Python with ADD9 in both cases, and here as well. ADD9. All other parameters you can keep as is. So exhaustiveness 8. So for real docking, you can choose different exhaustiveness. 8 is a compromise for relatively rigid compound. You have very flexible compound, you should choose more to have more trials to dock, because it's roughly the number of trials of docking, of searches. Then seed, random seed, number of poses, 3 poses, top 3 poses will be stored and returned, and number of CPUs. Here it says number of CPUs used for each molecule. So it depends on how many CPUs you have on your computers. You can specify from 1 to some large number, but this is per molecule, because we will have another argument where we specify how many molecules we process in parallel. here is a parallelization for each molecule. So yeah, a number of cores. So when you edit this file in Nano, to exit and save corrections, you have to type Ctrl+X, and then it will ask you, do you want to save? Okay, I can do this. Okay, and if you agree, then Shift-Y and enter. Shift-Y, and then enter that you want to save with the same name. So Ctrl+X, then Shift-Y, and then enter. And it will return you back. I will cancel this because otherwise I corrupt. So I will quit without saving, but you should save it. Yeah? And if your configuration file is correct, then docking will run very smoothly in one command. So let's go into the main command for which we are gathered here. So let's switch back. Okay. Here you can see some other specification. Currently doesn't matter. So we are just for demonstration purposes choose some different. And here is how to run docking. This command in the orange box, this is a single command which you can execute, and it will run both ligand preparation and docking sequentially. If you want only prepare ligand, you can run this part. If you want just to dock already prepared library, you can run this part. Just briefly explain. These are just few arguments which you may need most frequently. So as input, you specify SMILES or SDF of ligands, which should be docked. Then as output, you specify the name of the file with the extension DB, which would be your SQLite database. Then protonation argument is the for ligand preparation part. And here you can specify several options. Either you can type Chemaxon, MoGPK, PK solver. These are built-in programs, not built-in, but natively connected, I would say. So it's not necessary to install them somehow separately. But for example, for UniPK, you need to download a specific container because UniPK is difficult to install in the existing environment to not create a mess. So that's why we create a specific container which encapsulates everything. This container is available on all these computers. But probably we are quite short on time, so I would suggest that we can replace this protonation with MoGPK. And then here is a docking program. So we specify we want to use Vina. Then through the config argument, we pass this file with settings for Vina. And then we specify the number of molecules which will be docked in parallel. Yeah, here is, you can see 4. In our case, we have just one ligand in a SMILE, so it will still use only one molecule in parallel because we have only one. But if you will have more, 4 molecules will be docked in parallel. So roughly the number obtained by multiplication of this number of molecules by the number of cores specified in YAML file should be roughly the same as the overall number of cores on your computer, on your server, on a single server. Yeah. So these are 2 different parts, but they can be executed in one step. So preparation and docking. Yeah.
Said protonation tool is on PCs is available, but if I'm running on laptop, then I can also use
Yes, you can. I forgot to provide you the link to download it. Yeah, these are on Zenodo repository. But you can find the link in the documentation of EasyDock if you need this later. So you can go to EasyDock repository, then to EasyDock documentation. Just click and then go to the usage, maybe. No, here is no links. That's strange. Okay, advanced features. Containerized programs, configuration. I do not see no Zenodo. Yeah, pre-built containers. Yeah, here. Here in the section of container support, you can find the links to the Zenodo. I can copy and drop it to the channel, to the Discord channel. So this is the link where you can download this CIF file. So this container is a single file which incorporate everything inside. And in this way, you can easily integrate third-party tools. If you don't want to install it inside your environment, you can create this container and provide the path to this CIF file. Yeah, this container should satisfy some requirements, of course. So it should have some specific interface. But it is doable. Okay, so since we may not... Oh, shit.
And if we skip this automation step, then
No. Yeah, if you skip the protonation step, then molecules will be docked in the same format as input. This also enable you further tuning. So, for example, you have some other program or you have some idea about the protonation step. You create these protonation states outside of a EasyDock and do not specify protonation at all, and then these forms will be used as is. The protonation submitted to the program. Okay, let's see. No, tries to run Chemax on it. Fine. It's really funny. So we can copy this command, paste here, and instead of a CIF file, we can just type molgpka. And then we will replace unipka with molgpka. If you will dock, for example, I don't know, million of compounds, unipka will be too expensive, too slow. So that's why molgpk may be a better opportunity, but you should be aware that the protonation states predicted by molgpk will be worse, and maybe some top compounds which you selected based on this docking should be revised regarding the protonation state. So it may require some inspection.
TPK
For very large screenings, yeah, for small screenings, I would suggest to use UniPK. But UniPK container, it's something like 7 gigabytes. So
Yes.
yeah, you need some space, unfortunately, but it is more reliable. We try to improve it. Currently, we collaborate with Ostrava, with our supercomputer center. They help me to optimize this code because original code of UniPK is not that optimal, I would say. So we try to improve it. We already could pretty much make it much faster, but not enough. So, and type enter is doc not found because I didn't activate my environment. Okay. Conda activate crem add9, and then this command will run smoothly. So if you specify, yeah, these are some warnings from ModeGPK that, okay, some deprecated functions are used. Unfortunately, developers of this approach, they do not support often their tools, so that's why at some point these tools stopped working. So with some versions updated, or either you have to use old packages, old Python modules, or you will not be able to use them. So this is yeah, so in my case, the one molecule was already docked. So just one command.
Case the ModeGPK module is missing.
It should be. If it is missing, then something wrong with the installation of the environment, because it is installed automatically inside the environment. Yeah, so then conda list. No, it would be list. And then there is something problem with ModeGPK. Yeah, it's not here. It's not here. That's why it's easy. It's interesting how you install this environment. Did you use those environment provided from this repository, EasyDock Krem tutorial?
Following so it was missing here.
It's not necessary because
No, like
when you execute this command, it should install. Krem
Yeah.
and YAML, it should install it. If not, then I'm really
okay, maybe I
surprised.
missed this.
But otherwise, how you could install it without that?
So I just click this.
You can try, but currently you have it will not allow you because you already installed this environment. So either you have to reinstall it, or you can try to update conda update. I don't remember the exactly command. Conda env update maybe, and conda env update, and then pass to the file. Update without dashes, update, then -f, space, and the name of this environment files where it is.
Or
Because it is not in this directory, you have to whole pass to this file where it is located.
okay, I will try to figure out.
Yeah, that's really strange because this part always worked. What?
Does not work.
Something strange with the installation of the environment happened. So ModeGPK was not installed. So did you succeed? No. Why? Let's look. So you are not in that directory. Where did you stop? Even here, but okay. Let's go back. So you should be in this directory, and then you should execute all commands from this directory. And you already type
No, it's not.
this mk prepare. Okay, it should work.
This.
Yeah, this computer sounds so powerful, so it can. Yeah, it reports that it creates 3 files with explanation what are these files means, and you have these files in this directory. So just not lose your directory, your working directory. Yeah, it's in the beginning maybe a little bit complicated, but nothing really complex. And then you have to copy this command, this orange one, and replace. No. This select. I think that you have to select, then carefully click to not deselect it because you deselected. Then Control C, it's better. And then go here, right mouse. No, it doesn't work. Then okay, copyright, yes, and then okay, and then remove. No, remove this unit. Go by arrows. Yeah, left, and then remove this sieve image, blah blah blah. and type instead molgpk. Yeah, remove this one and this one and tilde and then no. And then molgpk. Molgpka. MOLGPKA. Yeah, that's A. Enter. Yeah, and it runs docking. So it takes this ligand, this smiles, output database. It will use the Vina with this configuration, protonate with molgpk. So it will take maybe 1 minute, just this ligand. So you succeeded. Yeah. No.
Yeah, it's actually the error from path. So maybe like this it will work. Right, like-
Okay, let's try.
I don't know if it should be a chain character or not, but
Oh, I usually always recommend to use absolute paths, not relative ones, but relative passes should also be acceptable.
I don't
We
know
can
how we do fast in nano. It's big.
right mouse button.
Oh, okay. We have the file. Okay,
Yeah,
nice. Just yeah. Okay.
and in here,
Same. So here.
yeah, it's not necessary to point still. Yeah, it should work. Let's try. So
Just save it.
Control X, then Shift Y, and then no, no, it's check keyboard. No English. Control X, Shift Y, enter. Yeah, it works. And now you can try this command with molgpk. Yeah, it should work.
One more purpose. So yeah.
Yeah.
For me, it works.
Yeah.
Okay. Nice.
So finally, just one command, but quite a long way to this single command. So it started, it will report you some service messages, some warnings. So do you succeed? Do you need some help with this? Okay, let's look. Yeah, one molecule were processed. So it means it's warnings. It's warnings from molgpkas because molgpks is not developed anymore. So that's why they use quite old modules, Python modules, and that's why when you install this old software in your environment, it reports that, okay, I use some old functions. Beware that in future versions, they will be deprecated completely. And this will stop working after maybe 2 years, I don't know. So you also succeeded? No, it's not a problem. It's just warning messages. Yeah, we can suppress them. We can suppress them. But in this case, I'm afraid that we suppress too much. And then if you have some real error, we will not know why it happened. So that's why it prints all outputs. So this should be managed on the level of individual modules. So developers should take care about this. But unfortunately, many academic software do not think about this. No, everything is okay. And did you succeed?
Yeah.
Yes. Cool. Nice. This means that this software works.
Yeah.
Okay. Yeah. Just a moment. Yeah. Oh, it's not necessary. It will be already for the tomorrow session. These are the single environment for both sessions, but this part actually you can do later. So it's not necessary now. But you could install environment already.
Yes,
So
I-
let's check. Maybe we can check. Try to activate it. Conda activate. It is activated. And did you try to run docking? Not yet.
Okay,
But did you already clone this repository? Probably. Could you open the PDF which I put into the channel in Discord? No, do you have Discord? Because I put this link to the Discord. No. No. You go to the Discord and it's very complicated. Oh. Then it's not necessary. I can, from my head, just find. If you, no, it doesn't matter. If you cannot log in, then we can find always workaround. It's always possible. You finally could do this. So there should be here, and then our session is here, and here is no, it's a Carol link. It's a repository. And here is a PDF file. So you can open it.
yes.
Just double click. Not very familiar with Linux, with Windows. So, and we go to this part to execute.
Yeah,
You executed this.
Conda.
But this git clone you already did also.
Yes.
Okay. In this case, we can go back to this one, yeah.
Yes.
And where is your directory? Okay, if it is not here, we can try cd easy. No, there is no such.
Oh,
Maybe. No. There is no. It's.
Yeah.
But. Yeah, some this installation. It's okay. It's okay. But this is installation of the environment. It's okay. I'm talking about git clone command. We have to find the place where you call this command. But okay, we can do this retrospectively. These are downloading. These are changing. Fine. Okay. Downloads. Okay. This is still CDP kit. Maybe dear open. Okay. Conda create. So there is I do not see. So Control C. We can Control R and then just type clone. So yeah, you call this, but it's not clear in which directory you call this call. We can do this in the downloads, for example, once more. So we can git clone.
Okay. And
It will. It doesn't work. Yeah. Perfect. Then we cd inside EasyDock, inside 9, inside 3 rounds. Here we see some files. These are gridbox. These are protonated. These are PDBQT format of the protein. These are ligand PDB. These are smiles. These smiles for further docking, but you don't have time for that. And these are config. And now you can just run this long command, but but this command you have to replace currently to be faster those protonation argument and type here more GPKA. These are model integrated inside. And okay, conda activate crem
Did before this
and conda activate crem ADD9 if it is installed, but it is not installed. It seems that there are some issues during the installations. Conda env list.
maybe
Or it's not list. Something like, yeah. No, it's there. So what happens? Maybe there is also some.
activate.
Ah, you have some special. You have some other keyboard. Okay. I didn't recognize that. Okay. And now you can execute this command with docking with more GPK. Yeah. Now it will work. Yeah, it's how to initiate database. We'll start the protonation. There are some. Oh. This is because we did not update the links. I told that we have to change the path in this YAML file to point out to your actual location, because if you use your laptop, your location will be different. And in this case, you can copy this path with right mouse, then nano config, and then replace this stuff with this new path.
Sorry.
Yes, exactly. This is a directory. Yes, it's a directory. And the same here. So we also remove all this. And again, insert. That's all. Control X, Shift Y, Enter. And now repeat. Now the database was already created. So LL, you will see 1 dB. So you have to remove it before. And then you can restart completely from scratch. Vina. So there were some installation problem during the setup of the environment. We can try to do this quickly. People. Yeah, I know, but if nobody against, again, people install Vina, and we can try. Yeah, enter. You can press enter from any position. Yeah, it's quite quick. And I again remove the database, and then restart the things. Maybe there are some other modules will be missed, but we can check. Protonation. It's okay.
Yes.
It seems working. So yeah, it works. So first molecule. Yeah, you're welcome. So we are out of time, unfortunately. So we didn't look how to retrieve data from this database. The command you can find in the PDB file. Just briefly. So Yeah, here are some examples of commands how to retrieve poses to SDF. There is a specific command get SDF from EasyDock, input database, output your SDF, and you will get the poses. All these commands have multiple arguments. You can type -h and see the list, a help message for all arguments, so you can quite precisely. Then another example, if you want to do this like a homework, docking of available CDK2 inhibitors. I collected 10 inhibitors with quite large difference in activity, so you can dock and compare the docking scores to the actual affinity of those ligands. I can say that it will be quite bad already. Then you can again retrieve poses. Here an example how to retrieve docking scores in SMILES format. So again, input database, output SMILE, then additional fields, ID and docking scores, and they will be extracted to the SMILES file. And the last part, what I wanted to show regarding the calculation of protein ligand interaction fingerprint, which are implemented through the ProLief. And this calculates those protein ligand interaction fingerprint and stores them inside the database. And this command retrieve these fingerprints to the output text file. So it's not necessary to have a PLIF extension. It can be whatever. It will be just a text table, large text table with contacts and 0 or ones, indicating whether you have contact or not have contact. And the last example, just to show how to easy integrate EasyDock in the Python software. So if you need just docking, nothing else, you can import docking function, moldoc function from a specific submodule for Vina, QVina, Gnina. We implemented many of them. Then submit your molecules with names to the docking function, specify which function used to docking, which configuration to be used, how many molecules should be docked in parallel, and that's all. And it will return you the mol IDs and the result where will be docking score, poses, and everything else. And we integrated actually this in different software in the some de novo generation software to generate structures guided by the docking scores. And it's really easy to do, just few lines of code. Sorry that we are a little bit out of time, so we didn't show. One more thing, just this database can be open and inspected visually. So it's not some cryptic database. It's like a file on your computer, on your server, which can be open. I will show you, for example, if you open this database for those 10 active compounds, it's not well visible maybe. Here you can see the IDs of molecules, input molecules, stereo IDs, input SMILES, curated SMILE, protonated SMILE. In some cases, you can see here the changed protonation states. And at the end of this table, you can see the docking scores, PDB, mol block, docking times, how much time each molecule took, and the time when the database, when this record was added to the database. So you can look this even visually. This SQLite browser, the link should be in the repository README, and it's installed on these computers, but never mind. So it's available for Windows, Linux, Unix, any platforms. So if you have some questions, I will be glad to answer, but I would suggest you just to rest before the next lecture, just to refresh a little bit, and see you tomorrow. Thank you.